Hello everyone and welcome. My name is Liz Kemper and I'll be your moderator for today's WJE webinar, Challenges in Below-Grade Structures, Relationships Between Waterproofing, Walls, and Shoring. During the next hour, WJE building enclosure experts Rick Mosco and Michelle Sandoval Marcinek will discuss the complex interrelationship between waterproofing systems, exterior concrete or shotcrete walls, and permanent or temporary shoring. This presentation is copyrighted by West Jenny Elstner Associates. And now I'll turn it over to Michelle to get us started. Michelle?
Hello, everyone. Thanks for joining us here today. We'll start off with just running quickly through our learning objectives. As Liz described, we're going to discuss common below-grade waterproofing construction assemblies, identifying different characteristics of shoring, waterproofing, and concrete wall types, and also get into how these different types of shoring and wall components can affect the performance of your waterproofing system, and also get into how to minimize problems associated with various combinations of below-grade waterproofing components. So now, Rick will start us off with a brief history of waterproofing.
Hi, everyone. This is Rick. Thank you for joining us. I just want to start off briefly by talking about the history of waterproofing a little bit. We did a little bit of research when we prepared this presentation, and fairly quickly we were able to go back about 2,500 years to find some interesting information. The Greek writer Herodotus, who's commonly known as the father of history, was known for traveling the ancient world and writing down his observations. And around 430 BC, he visited the city of Babylon. And during that visit, he noticed a massive construction project was underway. They were building walls and a moat around the city. And Herodotus was pretty fascinated by the method of waterproofing he saw. He reviewed it and he jotted down what he saw, and he said he saw hot bitumen with interposed layers of wattled reeds. And I thought, well, that sounds kind of familiar with some waterproofing we have today. So I went back a little bit further, and I was able to get back to 2500 BC. And in 2500 BC, the Great Pyramid of Giza was completed. In the 1970s, archaeologists exposed the original waterproofing on the foundation, and they noted that it was made up of a bitumen emulsion applied in coats with dry reed fibers applied in cross layers. So very similar to what Herodotus saw in Babylon. And it's important to note that every year the Nile River floods and it surrounds the pyramid, and these many of these tombs are below ground anyway. And when they were opened up in the 1800s, they found that these tombs were completely dry after all these years. The waterproofing had been very successful. So that's good news about waterproofing. The bad news is we don't have any 4,500-year warranties available anymore. So I want to turn it back over to Michelle, and she's going to talk about the typical components of below-grade structures.
Thanks, Rick. So to start off, thinking about a successful design for below-grade waterproofing depends on much more than just the waterproofing product you will choose. So first, we'll review some considerations for the other components of the system. And we'll start off with a few definitions. There are several terms you've likely heard regarding below-grade waterproofing. We hear positive side, negative side, and blind side. But these can be broken down as positive side being outside face, the side facing the soil, negative side, inside face facing your interior and basement space. And blind side is just another term to use for positive side waterproofing, which is placed prior to your wall being constructed. So the three components we will discuss today are the hole, as we affectionately refer to our site excavations, the wall, which is our structure, and the barrier, which includes the various waterproofing component options. So starting off with the hole, the size and shape of the hole we create on our site most likely will depend on one of two strategies, depending on whether it's backfilled or blindside application. So backfill conditions, if enough space is available, the decision might be made to over-excavate. In this case, the hole will be larger than the eventual footprint of the building, and after construction, soil will be backfilled in after our basement walls are constructed. Now, this is generally the most economical construction method, since shoring is to retain the soil if not necessary. The photo on the right shows a partially backfilled site with soil sloping down at a stable angle. Of course, this method requires more land due to the over-excavation. A benefit to this method is that we will have access to the positive side of our below-grade walls and can apply the waterproofing after the walls are constructed, giving much better control over the installation. In contrast, many urban sites do not allow the extra land required for backfilling. The owner likely wants the building to extend right up to the property line, and so the sides of our hole need to be completely vertical as well, requiring shoring to retain the walls, to retain the soil. This type of construction is generally more costly as shoring is relatively expensive to install. Now, for the purpose of waterproofing, we will still prefer our barrier to be on the positive side of the wall to keep water out. But since our walls are going to be right up against the shoring, we cannot install the system after the walls are constructed, like our backfill situation. Instead, this is where our blindside strategy comes into play, and we are attaching our product to the shoring so that the wall can then be built up to the waterproofing. And we'll end up with a barrier on the positive side. In the photo, you can see the waterproofing material has been nailed to the shoring wall, and the rebar is starting to be installed for the concrete wall. As you might guess, a disadvantage to this type of system is that we have less control over the final condition of the waterproofing, since it will not be accessible once the wall is placed. There's a potential for damage to occur during the installation of rebar and other construction activities. Now, for property line excavations, we generally need shoring of some kind. Before we review shoring types, there's an important concept to understand with shoring. The primary purpose of shoring is to stabilize our excavation. There are exceptions, but generally shoring is designed to be a temporary component of the structure. It's often made of wood, and while this is most likely treated wood, there's a lifespan of the material, and it will eventually decay. So an important consideration to keep in mind is whether any part of the permanent structure will depend on the shoring, which is supposed to be temporary. Now, getting into the various shoring types. First, we have soldier piles and lagging. The piles are steel, most likely wide flange shapes, driven into the ground at regular intervals. In between the steel piles, wood lagging boards are stacked to hold back the soil. Another type of shoring you might see are sheet piles, usually interlocking and also made of steel. Decant piles are another type. These are reinforced concrete piles that intersect to form a continuous shoring wall. Decant pile walls are reinforced with either steel, rebar, or with steel beams and are constructed by drilling in under the mud. There's also cutter soil mix, or CSM. In the photo, you can see that this example uses steel soldier piles as well, but instead of wood lagging, cement is mixed into the soil on site to form a solid surface. Pneumatically placed concrete, also known as Shockcrete, can also be used as shoring. In a few moments, we'll talk about how it can also be used for your wall construction. So you might have noticed in the previous few slides that shoring isn't necessarily a flat surface, which lends itself to simply hanging a sheet of waterproofing material. The surface of the shoring on your project is very important to consider when selecting an appropriate waterproofing type. A few examples of surface irregularities. On the left, our decant piles obviously have a very rough surface with limited options for waterproofing, but even smaller irregularities need to be considered. With our wood lagging in the other two photos, we have a 2-inch offset between boards where one of the boards has bowed, and even a 3/4-inch gap between boards like you see on the right, maybe more than what's allowed for certain waterproofing products. So all of this needs to be considered. Now, moving on to the next essential information we need to consider, which is the groundwater at our site. For our purposes, groundwater originates below the surface, as in the water table, and we'll refer to water that originates at the surface, such as rain or irrigation for landscaping, as nuisance water. Nuisance water may penetrate into the soil and flow down against our wall, but groundwater, on the other hand, may press against our structure with hydrostatic pressure, and it's a greater concern. If we're outside of the groundwater, waterproofing is less critical. In this situation, we may opt for no waterproofing or may opt for lighter duty with damp proofing. But depending on what the below-grade area is used for, it may still be desirable to install a robust waterproofing system. It really comes down to how much leakage the owner is willing to tolerate, which is usually not much. In contrast, if we are in the groundwater and subject to hydrostatic pressure, we're most likely to require a robust waterproofing system. If there's a standing water during construction, that will likely need to be pumped out to allow construction to progress. and in some cases, a site is permanently dewatered, which we'll talk more about shortly. However, it's not essential to prevent all leaks in every building, depending on the function. So as we've said before, it all comes down to how much leakage the owner is willing to tolerate. Temporary dewatering is usually accomplished with a series of pumps that remove water and potentially lower the water table during construction. The contractor is typically responsible for providing temporary dewatering during the construction process. On the structural side of things, it's important to take the hydrostatic pressure that will occur once the pumps are turned off into account, and to make sure the walls are designed to resist these pressures. Similarly, for the waterproofing, we'll expect that once the dewatering is deactivated, groundwater pressure will return and water may be pushed into the structure. So we would typically create a boat around our basement, with continuous waterproofing from below the floor slab to the top of the walls. The hydrostatic pressure will tend to push the building up. So again, structurally, it should be designed to resist this uplift pressure. Typically, the structural engineer, architect, and mechanical engineer have to work together to design a structure that will be able to withstand the anticipated hydrostatic pressure. Now, it may seem unlikely that water pressure would be powerful enough to lift a heavy concrete building, but this actually happened to a project that Rick and I have worked on. And luckily for all of us here today, this was captured on the security camera on site, so we can watch a time lapse of what this type of event looks like. Rick, do you want to walk us through what we'll see in the video?
Yeah, I'll take over here. I'm going to switch to the video in a moment. It plays automatically, so I'm going to wait just a moment. What you're going to see is you're going to see security camera footage of an excavation that was in Long Beach, California several years ago during a heavy rainstorm. In this case, we had one level of below-grade parking that had already been constructed, so the concrete walls were installed, the concrete floor, they were installing the columns on the lower level, but you can see into the lower level of the parking garage. You can also see the street on the right-hand side in a moment, and you'll see that there is an excavation between the building and the street. You'll also notice that on the left-hand side, when you get to the video, you're going to see a big black tank, and that tank is outside of the excavation, and that will be useful. I'll explain why in a minute. So what you're going to see in the video is you're going to see the rain coming down, the streets are flooding, and you're going to see water start to pour in from the street into this excavation between the street and the structure. And you'll watch this ditch fill up with water, and then all of a sudden you're going to see the water level drop dramatically, very quickly. And then at the moment that happens, focus your eyes on the inside of the structure, and what you're going to see is there are a lot of things stored inside this garage. You're going to start to see this building lift up. And in fact, the building lifts 26 inches because the water gets underneath and exerts so much force on the building that it lifts this concrete structure up. So we're going to move to the video now. We're going to run it a couple of times. So you see the ditch filling up there, and it's getting high, and the water drops down enough. You look at the left, you see slowly the building, all the things in the building are lifting. And you can tell they're lifting by looking at them relative to that black tank and to the excavation, the shoring on the right-hand side. There it goes down, and you see it lifting again. See all that area go? It's pretty fascinating. It was very surprising, and lucky we had it on video. And one last time, and then we'll move on. You can see that building lifting. Again, 26 inches was the increase. Turn it back over to Michelle.
Thanks, Rick. So as we mentioned, another strategy for some sites in the groundwater is permanent dewatering. In this case, we are relying on active dewatering of the site for the life of the structure. There are several things to consider with this approach. Obviously, the pumping equipment has to be very reliable. Some municipalities do not allow permanent dewatering, and in some cases, filtering and monitoring of the water are required before it's discharged back into the storm drain system. But if permanent dewatering is an appropriate option for your site, waterproofing at the walls will be less critical. We'll mostly be concerned with nuisance water, and if we're lowering the water table below our building, waterproofing at the floor may not be required at all. So now for our next component, our below-grade structure is the wall. Below-grade walls can be made of masonry and other materials, but we're going to focus on concrete walls for this discussion. The traditional type of concrete construction is poured into formwork. The photo here is showing formwork in a backfill condition. The traditional formed concrete can also be used in blanket applications, with perhaps the shoring used as one side of the form. There are some advantages to formed concrete over shotcrete, which we'll discuss in a moment. One of them is that form concrete allows for conventional consolidation techniques. And this means that the aggregate and other components of the concrete mix should be well distributed, which is helpful in avoiding surface irregularities in the wall. And we'll discuss more about how surface irregularities can affect waterproofing. Also, in terms of backfill conditions, CMU walls will be similar to form concrete in that waterproofing can be applied directly to the wall on the positive side once the wall is in place. Now, Shockcrete has been around for a while, but it has really taken off in the last few years for below-grade wall construction. The main reason being it tends to be cheaper and faster than placing traditional form concrete. We generally see Shockcrete applications on blindside applications, but it can also be used in backfill conditions if one-sided form is installed. Now, it's important to know that Shockcrete isn't a good fit for all below-grade waterproofing products. Some products are designed to work with Shockcrete specifically, but many others are not. If you learn that Shockcrete is going to be used for the below-grade walls of your project, make sure to understand the implications and choose a system that will be warrantable for this type of construction. Some issues that we see with Shockcrete are consolidation issues. Since Shockcrete is sprayed onto the rebar and has to remain in place, it can't have the same flow that you'll see in form concrete. It tends to be a stiff mix. This can lead to voids as it's more difficult to make sure this thick mix is filling in all the nooks and crannies of the wall. When you have a thick rebar cage like in the photo, you may also have voids behind the steel rods where, again, the Shockcrete is having difficulty flowing and filling in behind. This is called shadowing. As with many things, a successful installation is highly dependent on the applicator's skill level. And now Rick is going to review the various types of materials commonly used for the barrier component of our system.
Thank you, Michelle. So we're going to talk a little bit now about the barrier. And of course, as most of you will think of the barrier, that's really what we're talking about when we say waterproofing. In order to select the right barrier component, you really have to consider all these things that Michelle's been talking about. You need to take into account the groundwater conditions. There will be some systems that are more appropriate in the groundwater, some that are maybe less effective in the groundwater. You also need to take into account your excavation type, whether you have a backfilled installation or a blindside installation. If you're using shoring, we need to take into account what type of shoring it is, because some materials are going to work well with some shoring and some will not work with those. And we'll also take into account the wall construction type. As Michelle mentioned, some systems don't play well with Shockcrete, so we'll want to take that into account. You also want to take into account soil and groundwater contaminants that might occur. Here in Los Angeles, we do work around the La Brea tar pits, and as you can imagine, dead dinosaurs create some hydrocarbons that can be pretty aggressive to some waterproofing materials. And as Michelle alluded to a couple of times, tolerance for water intrusion is important. And we say that because when I go to a meeting with a client, sometimes I'll ask them, how much water leakage are you willing to tolerate in your garage? And usually they laugh at me, they think I'm joking. But I'm really asking a serious question. It does cost more to have a more reliable waterproofing system, and you can get by with less if you don't. So how important really is it? So the picture here on the left is a relatively moderate leak. I would say this happens to be coming through a penetration in a wall. And that certainly is very noticeable. It's not creating any safety hazards, but it's something a lot of clients would not be happy with, a lot of building owners would not be happy with, a lot of designers wouldn't be happy with. But you think about it, if you took that same parking garage and built it above grade, as in the picture on the right, we wouldn't even put walls on it. And every time it rained, water would come flying in and nobody would complain about it. So it is important to discuss with whoever is going to be operating this building how important it is. If this were a retail center, for example, nobody stops going to a department store because they saw water leaks or water stains in the garage. But if you're going to a condo and you're planning on buying a $1 million condo and you see water leakage, you're going to get the impression that the building is of poor quality. So again, it depends on the actual needs of the property. So for our continuing discussion of these different systems, we're going to limit ourselves to talking only about positive side waterproofing, as Michelle mentioned earlier. And we're going to consider some materials that are appropriate primarily for post-applied or backfill conditions. We will also look at some materials that are appropriate for pre-applied or blindside conditions. And then there are some materials that can actually be used in both conditions. And then we'll talk a little more about the limitations that are placed on a waterproofing membrane if you use Shockcrete. So we're going to start out with our first type of material. We're going to talk about fluid-applied membranes. And these are usually materials that are asphalt or polymer-based. They're usually applied to the wall in backfill applications, or they can be used being applied to shoring in blindside applications, depending on the type of product. Because these are fluid applied, they can be applied using sprayer, roller, or trowel sometimes. They do have risks associated with them. You do have a little additional installation defect risk because everything is being determined in the field. The thickness of the material is determined by the applicator, but you also need to take into account the condition of your substrate. Make sure that your walls have the right finish. Make sure they're smooth enough for whatever material you're using. And make sure they don't have any contamination on them. They usually require a relatively smooth, flat substrate. So the picture you see here, that orange material is a fluid-applied waterproofing membrane. And in this case, it's being applied directly to a CMU wall, but it could be to concrete. And this material bonds tightly to the substrate, bonds tightly to the CMU or concrete. And that provides us a pretty big advantage because if there were to be a breach in the membrane, some pinhole somewhere, and water were to get through that membrane, it probably won't get into the building unless there is a crack or a hole in the concrete immediately where that hole is in the membrane. And that's because the tight bond of the membrane to the substrate prevents water from migrating laterally. It can't travel in a space between the wall and the membrane to find a new location where it can penetrate the wall. This is an example of a fluid-applied membrane in a blindside application. So what they're doing here is they're applying the fluid-applied material to a carrier sheet. In this case, it's a drainage mat. And the drainage mat is mechanically attached to the shoring, and then the fluid-applied material is sprayed onto it and integrated with those steel piles with the fluid-applied material. Now in this case, the issue is that this fluid-applied waterproofing is now not going to be adhered directly to your concrete wall. And because of that, if water were to penetrate this membrane, it would have the ability to travel laterally between the membrane and the wall. So once it punches a hole in that membrane, it can find some small flaw in the concrete wall and then find its way into the building. Another issue with materials that are not adhered tightly to the building concrete wall is that if there is movement, differential movement between your shoring and your building wall, that creates gaps, and the gaps can also present some problems for our waterproofing systems. The next type of product that most people are pretty familiar with is the adhered sheet-applied material, or we call them often peel and stick. And this type of system is not suitable for pre-applied applications. It really needs to be a backfilled condition. These materials can adhere to the substrate, and they can adhere pretty nicely. They can adhere pretty tightly, but they have some critical elements to them. They do have seams that must be lapped. They must have a very good substrate, very smooth substrate. The substrate must be clean, and if you have all of these conditions that are suitable, then you can get good adhesion. And once you get good adhesion, again, you have the ability to limit lateral migration of water if it were to breach the waterproofing membrane. The next system we're going to talk about is the adhered thermoplastic sheet. And this is a thermoplastic sheet that is usually installed against the shoring. And this material adheres tightly to the concrete when the concrete is placed on top of the membrane. And usually it adheres because of mechanical properties. It's either got adhesive or a rough surface that bonds nicely to the concrete. And this usually gives us a very good, very tight bond. And again, we're limiting the migration of water if the membrane is breached. Again, that makes it very difficult for water to actually leak into the building, even if it penetrates the membrane. Now, because this is attached and adhered tightly to your concrete wall, it's not really significantly affected if you get differential movement between your building wall and your shoring wall. The next one we're going to talk about is unadhered thermoplastic sheets. These are usually mechanically attached to the shoring on a blindside application, and the mechanical attachments nowadays are sealed. They're made in such a way that they can be sealed, so they'll pose a major risk of leakage. But these materials are also commonly used as a secondary membrane in a dual membrane, and we'll talk about that again in just a few minutes. The next product we're going to talk about, and a lot of people have seen this many times, is the unadhered hydrophilic sheet. So these can be used in both blindside and backfilled applications. It's one of the systems that works in both applications very well. Hydrophilic materials may be made of sodium bentonite or a polymer. And what these materials do, what hydrophilic materials do, is when they get wet, they expand, or they try to expand. And they will typically expand anywhere from 8 to 15 times their original size when they're exposed to moisture. If they are confined and held in a tight space, they are not able to expand. And so what happens instead is this material becomes more dense. And when it becomes more dense, it becomes waterproof. But again, that requires this tight confinement. If for some reason we don't have good confinement of these materials, and when I say good confinement, I mean that on both sides of this material, there has to be a solid substrate that does not allow this material to expand more than about 1/2 an inch. And if you can achieve that, then you're also going to be able to limit lateral migration of water just because the pressure exerted by this expanded material does press up tightly against your building wall. This is a little experiment we conducted in our office. The left-hand photo is a sheet of bentonite in this case. It's probably less than 1/8 of an inch in thickness. In the middle picture, you can see that we've filled the beaker with some water. And later on that day, you can see that this material has expanded probably 8 to 10 times its original thickness. So it's trying to expand. Again, if you were to take that expansive material and confine it into a space that did not exceed about 1/2 an inch, that material will become very dense, and that makes it very waterproof. Now, lack of confinement is a problem for these materials, and that can occur in a variety of different ways. And one of the ways we talked about a few minutes ago was movement of a building wall after construction. You can see the diagram here. It shows a 2-level below-grade structure, and you can see that the top of the wall is pulled away from the shoring. Now that can be minimized with some certain design and construction techniques, but this is a fairly common problem. And when you have that, you have a couple things that occur. First of all, you no longer have confinement for a hydrophilic material, not sufficient confinement. And you also have a big gap that can allow debris and materials to flow into your gap there, and that could damage the membrane also. A little video here showing how that's made. We'll create our excavation, put in our shoring, our foundations, and then we start building our walls. And what happens is as you add subsequent floors at the intermediate level and the top level, those concrete floors shrink. And as they shrink, they pull the walls away from the shoring. And that's how we get that gap. Inadequate confinement can also occur because of billowing of the membrane. Now, you know, if you take any sort of sheet and you hang it against a flat wall, it's never going to lay flat against the wall. You can see in this photograph the shadows on this waterproofing membrane, and that's showing how it is billowing. This is a picture of that same installation. You can see the photo on the left. I measured the position of the waterproofing membrane, and it's off of the rebar about 1.5 inches. But just by pushing my tape with no other force other than that, I was able to expand that gap to 2¼ inches. So that gap behind that membrane is 3/4 of an inch. And as I mentioned before, for most of these systems, 1/2 inch is going to be your maximum gap that you can get away with without having a potential failure of your hydrophilic materials. There's another picture. This is even worse. In this case, the membrane is actually touching the steel rebar. Now, this is not only a problem for us from a waterproofing standpoint because there's probably at least 1.5 inches or more of gap behind that membrane, but your structural engineer is also not going to be very happy with that because you don't have enough cover to protect your rebar. Now, this could be taken care of with proper installation techniques. In the photo on the right, you see a little concrete block there in the lower portion of that. That's called adobe. It's a concrete block or some other material, and it's tied to the rebar. And it is designed at a certain width so that it will push the waterproofing back against the shoring and make sure you have proper setback from your wall for the rebar. The problem with this is these adobies are installed by the rebar installer, And he doesn't really care about the waterproofing. So he's going to be locating these where they're necessary to get his rebar in the right place, but he's not going to be going around looking for those areas where the membrane is billowing. So that's a fairly significant potential problem. Here we can see an example of a board-formed concrete. So we have a form on the right, we have the shoring on the left, and we're pouring in liquid concrete into our membrane. You can see that the billowing is now being pushed away. As the weight of the fluid material fills the cavity, it pushes the membrane back up against the shoring. So if you're actually doing formed concrete, you can minimize that problem pretty easily. In the case of Shockcrete, we don't have that ability. The fluid applied weight doesn't really occur. And so what happens is when you apply the Shockcrete, it really doesn't push those billows back against the membrane. So you can have fairly significant amounts of excessive gaps in there. It's not unusual when investigations are done of these structures to find 20 to 25% of the wall has inadequate confinement for hydrophilic material. Another possible problem is inadequate consolidation of your concrete. This is a picture you saw before, and this is a Shockcrete wall that was shot up against a form. Normally, the face you're looking at would be up against the lagging, so nobody would ever see this, and you wouldn't even know these gaps occurred, but these are pretty large gaps. The reinforcing in this picture is 5/8 of an inch in diameter, so these gaps are several inches wide. And because you have these big gaps, where these gaps occur, you cannot get proper confinement of your waterproofing. So that's going to be a problem with Shockcrete that's particular to this type of material. Now we talked about the movement of the walls, we talked about voids in the concrete, and we talked about it relative to how it affects confinement of your hydrophilic waterproofing, but these are also problems for other types of waterproofing. If you have an installation where you are in the water table and you have that severe hydrostatic pressure that we saw exert that so much force in that video, if you have areas where your waterproofing membrane is not being adequately supported by your building wall, the pressure can actually blow out the seams in your waterproofing membrane if there's a gap on the wall side, or it can actually blow out a hole in your waterproofing membrane because that force is so significant. Another issue we deal with, especially if you're using wood lagging, wood is wood. It's not going to last forever. There are hundreds of different treatments you can use on wood to make them last longer. They vary in longevity, but wood is not going to last forever. So if you are going to rely on wood lagging to maintain your confinement of your waterproofing, you're probably not going to get as long a life as you would out of some other type of material. This is a perfect example of where shoring is really temporary. And now we're going to get to the composite sheet. So we talked about hydrophilic materials, and we talked about unadhered thermoplastic sheets. So this is a combination of the two, where we're taking a hydrophilic sheet and a thermoplastic sheet, and we are marrying them together. And this has a lot of advantages because you have the hydrophilic sheet as your backup, but your primary membrane is going to be your thermoplastic sheet. So typically, the thermoplastic sheet is applied against your shoring, and it is going to be mechanically attached. And then, because you're going to have holes in this membrane, you have a potential location for possible leaks. But what happens is, once a leak occurs in the thermoplastic sheet, it reaches the hydrophilic material. And if the hydrophilic material is properly confined, the water will activate the hydrophilic material, it will expand, and it will literally seal the hole. So it's kind of a two-stage protection of your installation. Where you do have holes, we try to improve the performance of that. Here you can see a nail that is being used to attach your rebar, and you can see there's an extra piece of material there. That is a bentonite-based water stop. It's the same material as the bentonite waterproofing, and they simply drive the penetration through that. And so what happens is, knowing that water is going to get through that hole, the water will reach this hydrophilic material, the hydrophilic material will expand, and it will literally seal our hole. And then our final system we're going to talk about is we're going to talk about, in general, specialty systems that are designed specifically for shotcrete. As we said, a lot of these materials we talked about don't perform well with shotcrete for a variety of reasons. So as shotcrete has become more and more popular in the marketplace, we're seeing more manufacturers create products that are designed specifically for that product. Like I said, there are a number of them. This is one of the ones that have been around the longest. This is a proprietary system, as most of them are. This is the one we have the most experience with. It's kind of a unique installation. What we've got going on here is the shoring has a carrier sheet that is mechanically attached to it, and that carrier sheet is really nothing more than a mesh. There's no waterproofing to it or anything. It's just a mesh, and it is attached to your shoring. Then your rebar installers come in and they install the rebar cage. That's what we see here in this photograph. After the rebar is installed, then the waterproofing contractor comes back and he installs tubes, injection tubes, that are attached to this mesh carrier sheet on the shoring. And these tubes extend out beyond the eventual face of that concrete wall. So here you see the concrete wall, and you can see the tubes sticking out. And after this is done, now at this point, this wall has no waterproofing in it at all. What they're going to do now is go back and inject in each of these tubes a waterproof resin. And this waterproof resin will fill the gap between the concrete wall and the shoring wall. And it does a lot of things that are very helpful. First of all, it bonds very tightly to the, let's go back here. It bonds, let's see, there we go. It bonds very tightly to the concrete wall that's cast against it, but it also can fill any voids in your shoring, and it can fill any voids in your concrete wall. So if you have voids in the shotcrete, this waterproof resin will fill those voids, and it will solve a lot of the problems we saw in other conditions. So that's pretty much the end of this. We're going to go to our summary and talk about what we've learned so far. We'll talk about the considerations. Decisions related to your below-grade waterproofing need to take into account a number of interrelated factors that Michelle and I have talked about. You need to think about whether the below-grade structure will be in groundwater. We need to know if there are any soil or groundwater contaminants that might affect your selection of materials. We want to consider how much water intrusion, if any, is going to be acceptable, because that will have an effect on the types of materials we want to select. We need to consider the budgetary limitations. What are the things that might affect our decisions as far as how much cost we can have? Again, as I mentioned before, typically more reliable systems are going to cost more money. So if there is money to be saved, that might be a place to do it. We need to consider the site limitations that will drive the excavation type. Do we have enough room to do a backfilled installation, or do we have to go all the way to the property line and do a blindside? It's not uncommon for some projects to use both. They might need to be blindside on some of the sides, but there may be room on other sides for a backfilled condition. And that adds some new complications because, as I mentioned before, some of these systems are appropriate only for blindside. Some are appropriate only for backfill conditions. So now you have to consider how you're going to transition from one to the other. You need to think about what type of wall you're going to have. Is it going to be formed or concrete? As we mentioned before, shotcrete walls present some unique problems for many waterproofing systems. And we need to just figure out which of these conditions apply most for our project and make sure we're taking them all into account. We're going to close out right now with a very brief quote from a famous American. This dapper gentleman is Conrad Hilton, and he was the founder of the Hilton hotel chain. And one day somebody asked him what the most important thing was that he learned in all of his years in the hotel business. And his answer was, the shower curtain goes inside the tub. I'll turn it back over to Liz for questions.
Thank you, Rick, and thanks, Michelle. Okay, our first question is, what are the toughest blindside detailing conditions that you typically encounter?
Okay, yeah, that's a good question. There are a number of unique conditions that can occur in blindside installations, and it's hard to say which is the most difficult, but some of those would include, as we saw in most of our pictures of shoring, we saw wood lagging on what I would call the interior building face of the steel pile. Sometimes the lagging is actually on the other side of the steel pile, and therefore that steel pile is now going to be encased in your concrete wall. That presents some unique challenges because now your waterproofing membrane can't go past and through the steel pile. So now you have to terminate your waterproofing on the steel pile with a reliable seal, and that can be difficult. We have one project we're looking at right now where we actually have a normal installation with the waterproofing going in 2 stories at the interior face of the wall, and then it actually jogs back to the back side of the steel pile for the 3rd floor. It's a very unique situation. So that's difficult. That's probably the most difficult situation I can think of offhand.
Okay, our next question. How did you solve the issue where the building was raised 26 inches, and where did the water come from?
So what happened there is, as you saw water entering the excavation there in that gap between the building and the street, what happened was that so much water filled up that gap that there was so much head pressure, it actually pushed the water underneath the floor. Now that site that's in the groundwater, so that site actually had temporary dewatering. But the amount of water that accumulated because of this severe rainstorm far exceeded the ability of the pumps to pump the water out. So it pushed its way underneath the floor of the structure and then lifted the structure at 26 inches. In that particular case, what happened was we were engaged to investigate a number of things. We investigated the structural condition of the building because it cracked quite a bit, and we investigated the condition of the waterproofing underneath. And then the geotechnical engineer had to investigate the condition of the soil underneath for support of the structure. In the end, we all determined that it was possible to reuse that structure. And so they continued to build, I think it was another 7 stories on top of that structure. And they were able to successfully perform that. The downside was because we couldn't be sure of the waterproofing, damage to the waterproofing, we did not get a warranty for the waterproofing, but instead we put money aside for localized repairs.
Okay, our next question. What kind of warranty is possible with blindside waterproofing? If waterproofing fails, what remediation or repair is possible, and how is responsibility assigned?
So, you have a lot of options when you're selecting a waterproofing system as far as what kind of warranty you want. And the type of warranty you get will depend on a number of factors. Sometimes you pay an extra fee, but most importantly, there will be more attention paid to the actual installation. So for a very high performance warranty, where there is very little risk to the owner of the building, there will be a fairly high fee for it, but then there will also generally require very aggressive inspection of the work as it goes on. Sometimes even full-time inspection. And so with these enhanced inspections, we can be a little more sure that we're getting a good installation. But again, with blindside, you never really know what happens once you get your wall built. So those kinds of things can pose a problem. As far as the warranties, we generally don't have a lot of trouble with most manufacturers living up to their warranties, of the major manufacturers that we do business with. And normally what happens is, first of all, you have to determine exactly what the cause is. Again, we noted a number of different causes. We noted that it might be that the building wall is moving separately from the shoring. It might be that we think there are voids in the concrete walls. So, well, first of all, we want to find out what the problem is. That'll make it easier to address. But most of the time when we have failures, you're able to make repairs by drilling through the wall and injecting either a curtain of waterproofing material to replace the waterproofing membrane that was damaged, or you can fill the cracks. If the water is leaking primarily through cracks in the concrete wall, you can seal those cracks, and that usually will have an effect on reducing your water leakage. Now, this type of repair is something that almost never works the first time you try it. It's an iterative process, so they'll usually go in and they'll repair the areas that are leaking now, and then after they do that, the water finds the next path of least resistance, and it will start leaking again, and you'll go and repair those. So it's not uncommon to take 2 or 3 trips back to make those repairs. But usually we can get repairs made if it's a properly designed, properly installed system overall, we can usually get those repairs to work.
Okay, our next question. In areas where a boat approach is required, compatibility between vertical and horizontal waterproofing becomes important for continuity. Do you have any recommendations for waterproofing types to be used for both horizontal and vertical applications to achieve the boat?
Well, there are a lot of different systems available, and again, systems will have to be designed for underfloor and or wall applications, and they'll have to be designed for groundwater conditions. And it depends on the manufacturer. So, for example, many of these dual hydrophilic sheets, the dual membranes, those materials can be used either both in the wall and under the floor. And so the same material is used. In fact, that's what was used in that installation we saw in the video where the building lifted. That was a hydrophilic dual membrane sheet. And so that's one way. Other systems, one manufacturer, you want to use the same manufacturer because you want to maintain warrantability. But some manufacturers will have a slightly different material they use under the floor compared to what they use on the walls, but they have pre-engineered integration designs for those. So,
yeah. Another thing that comes up often is you may have conditions where you have backfilled walls and blindside conditions within the same project. So that's another condition where detailing of those transitions are very important. And you also, again, like Rick mentioned, it's important to be able to have consistent manufacture between those products so that transitions are compatible. And if you're using different manufacturers, you have to make sure both can agree on what detail will be used at that transition.
And if I can go back and talk about warranties, the question, I guess I didn't really answer the question in total, but it's possible to get anywhere from a 5 to 20-year warranty on various waterproof membranes depending on the system and how well it's installed.
Okay, our next question. What is the composition of a carrier sheet?
In the application that I showed in the example, that was a drainage board, basically a drainage composite, and that is a dimpled piece of plastic that has a filter fabric applied on the opposite side. And what that does, and we didn't go into a lot of detail about drainage composites in this presentation, but that's a commonly used component in waterproofing systems. It creates a gap that allows water to drain so it doesn't sit against the building wall if you're not in the water table. So in this case that I used as the example, the carrier sheet was a drainage board, and the waterproofing membrane is spray applied to that drainage board. Now the drainage board, of course, comes in sheets and they have lap seams. So in that particular manufacturer's design detailing, they use a reinforced fabric over all of the seams in the material that is embedded in the waterproofing, and they also use a similar reinforced mesh that is applied over all fasteners so that you can seal the fasteners.
Okay, our next question. How would you efficiently evaluate installation on blindside application post-construction?
Well, about all you can do is look for leaks. There isn't a whole lot you can do after it's installed. If you have leaks and you're concerned about what the cause is, then of course there would be some forensic investigation that would probably take place to determine what the cause is. And that would involve drilling some holes and taking samples and a variety of efforts like that.
Okay, our next question. At what distance from a property line would you decide you need blindside shoring?
Well, it depends on the location, and again, because of the limited time we have for this, we didn't go into a lot of detail on how those shoring walls are installed. But when you have steel soldier piles and wood lagging, if you're extending more than about 8 or 10 feet from the bottom of the excavation, you probably aren't going to get enough support just by cantilevering these steel beams. So you have to find a way to keep those beams from deflecting from the pressure of the soil into the excavation. Normally what they'll do is they will use what they call tiebacks, and that's they drill a diagonal downward hole into the soil outside of the property, and then they'll install a concrete encased rod or cable in there to keep the wall in place. Now that would cause you now be installing materials that are outside of your own property line, and that may or may not be possible depending on the legal ramifications of that. Without that type of an issue, normally you can take these soldier piles and put them all the way up. Normally they go within maybe 2 or 3 inches of the property line just to give them a little bit of room, but that either way it requires a lot of consideration. When you're doing this, there's another thing to keep in mind too, and that is if you are installing a new excavation and there is a building adjacent to you, you now have to take into account the pressures this existing building might be exerting on not only your shoring but also the excavation process. So you have to take that into account and not get too close to other buildings. But a couple of inches is usually enough for that. There are some cases where when you're in a public right-of-way where the city might allow you to actually install your soldier piles within their right-of-way. That's not quite as common, but we see a little bit of that out here.
Okay. Excuse me. Our next question. How do you prevent cracking in concrete due to hydrostatic pressure? Can the waterproofing system prevent this? Well,
your concrete walls are typically going to crack no matter what. At least in my experience, we don't normally see control joints in below-grade concrete walls. They're continuous. And because they're continuous, they're going to crack, and so we anticipate seeing the cracks. As long as you have a good, solid waterproofing membrane, the cracks in the concrete wall shouldn't be a problem. It's just part of normal concrete behavior. The waterproofing membrane is what's doing the bulk of the work in keeping the water out. So we don't really, obviously you don't want to have huge cracks in your wall, so proper mix design, proper reinforcing, all these things are factors that can play into making sure you have limited cracking on your concrete wall. But the cracks themselves are not necessarily the problem if you have a good waterproofing system.
Okay, our next question. Do any of the systems you described have difficulty with transition to above-grade waterproofing?
Most manufacturers of below-grade waterproofing have approved details for transitioning to above-grade details. And unlike the below-grade systems that we talked about how important it is to have materials from the same manufacturer to enhance warrantability. It is not as common, not as necessary to have your above-grade waterproofing actually be from the same manufacturer as your below-grade. There are advantages to doing that, but it's not really necessary. There are a lot of transition details that can be used. Many of them utilize some sort of sheet metal flashing. We call sheet metal flashing the universal transition material. Almost everything transitions to sheet metal. So if you can take one product and tie it to sheet metal on one side and another product and tie it to sheet metal on the other side, you now have a good solid transition. But there are a lot of manufacturers allow other manufacturers' products to come in contact with their product at these types of transitions. It just depends on the product.
Okay. Our next question. If Shockcrete is utilized and there are large gaps or unfilled pockets similar to what was shown in the presentation and the basement is leaking, what would be the remedy?
Well, the most common repair we see in those cases is some sort of injection, either injecting the wall to make the wall more waterproof, or injecting materials into the cavity that's occurring on the backside. There's a problem with that, though, if you're not in the water table particularly. First of all, when you're injecting through the concrete wall and you're trying to put a waterproof material grout on the other side of the wall, you have very little control over where that grout is going to go. So trying to get a complete uninterrupted curtain on the backside is very difficult. Also, if you are in a condition where you're not in the water table and you have a drain board or this drainage composite, the drainage composite has a nice gap in it, and that would make a great location for you to fill this gap up with a waterproof material to make it waterproof. The downside is now you don't have proper drainage, so now you're going to have water accumulating against your wall, and now you have to judge whether it's more important to get the waterproofing solid or if it's more important to allow the water to drain. And it just depends on the specifics of the circumstance.
Okay, our next question. Is it okay to have waterproofing on the negative side of shoring and the positive side of a foundation wall with a 5-inch gap between them? or actually that says 5-foot gap between them? And will the water trapped be an issue?
I'm trying to understand the question. Repeat the question again for me.
Yeah, sorry about that. I tripped over it. Okay, let's try it again. Is it okay to have waterproofing on the negative side of shoring and the positive side of a foundation wall with a 5-foot gap between them? Will the trapped water be an issue?
So are we talking about waterproofing on the building wall also? Are there 2 layers of waterproofing, or are we talking about, I guess I'm having trouble following the example, but it sounds like you have waterproofing on the shoring, and then you have a gap, and then you have the building wall. So it just depends on how water might get into that gap. If water gets into the gap, you're going to have a problem with it getting into the building.
Okay, our next question. During construction, what is an acceptable amount of prehydration of a hydrophobic material, and how is it evaluated?
Generally, when that occurs, the activation of the hydrophilic material will cause it, as I said, will cause it to swell. If it swells more than about, double its thickness, if it's 1/8 of an inch and it swells to 1/4 of an inch, you might have some potential problems. Normally what happens when this occurs, and it happens periodically, you'll leave something out in the rain, it'll get very light rain on it, you'll get very minimal hydration, and then what you do is you have your manufacturer come out and approve it to make sure that it's still going to be warrantable. And that will depend on the specifics of the manufacturer and the type of product it's using. What happens if it gets severely hydrated and starts expanding is that if it's not being confined, it can actually crumble and fall away from the wall. And then you have no waterproofing in that location at all. So it really is a matter of inspecting to see the level of damage that's occurred from the situation. Like I said, normally most manufacturers of hydrophilic materials don't really want to allow it to expand more than about 1/2 an inch. So if you are under 1/2 an inch, you're probably in decent shape of getting a manufacturer to approve it, as long as it's not falling apart, as long as it's not coming off of the carrier sheet.
Okay, we've got time for one more question. How does temperature affect the waterproofing installation?
Well, it depends on the system. We talked about the condition of billowing, for example, of these hydrophilic sheets. What we found in trying to mitigate the problem is if you can install them in relatively warm temperatures and then come back and apply your concrete after the temperatures have cooled down, what happens is the billowing, the sheet itself will expand in the warm weather, and you'll see the billowing because of that. But then as the material cools, it starts to shrink a little bit, and when it shrinks, it gets a little more tight to the wall. So that is one of the techniques that we recommend for minimizing billowing on these Blindside hydrophilic sheets that are installed. Otherwise, there's not a lot of issue with temperature on those materials. Some fluid applied materials could be a problem depending on the application. If you're applying to concrete when it's relatively cool and then it's warming up, what will happen is you'll start to get off-gassing from the concrete, and that might cause bubbling of your fluid applied material, blistering. So it's usually better to apply fluid applied materials to concrete when temperatures are becoming cooler, not warmer.
Okay. Rick, Michelle, thank you so much for the great presentation. And if you have any questions about today's presentation, please reach out to Rick or to Michelle. If you have any questions about WJE webinars, please reach out to me, Liz Pimper, at lpimper@wje.com. So again, thank you so much for your time, and we hope you have a great rest of the day.